to just look at an expression for the electric and magnetic field inside a waveguide, or you can say it is a general expression. It is not you can generalize it to an expression which is inside a waveguide, transmission lines, etc. But before we go or we look into all these things, let's first understand what's the basic difference between a transmission line and a waveguide. Okay, so the electromagnetic wave, as we have seen in the last few lectures, we have seen the wave is propagating in an unbounded medium. That the wave doesn't have any kind of restrictions in propagation. That's called as an unbounded medium. And then we had looked at when the wave meets a boundary. That means it is trying to pass from one type of a medium to another type of a medium. It will encounter a boundary, and at that boundary, what all things will happen, like normal incidence, oblique incidence, etc. So all these things we have seen. Now, when this unbounded medium in which the EM wave is propagating, now if the medium is made bound, for example, let's say I have a transmission line. Now, the simplest example of a transmission line is a coaxial cable. So in coaxial cable, you have an inner core, and then there is an outer core, something like this. Okay, and the wave is propagating through a medium in between these two. This is one kind of transmission line. It's a coaxial cable. Okay, this is a transmission line. It's not a waveguide. Now, when the wave propagates, we have seen the expression of what is the expression of voltage, what is the expression of reflection coefficient, how much wave will be reflected. If you connect a load, how does it affect the wave, etc., etc. in our first few lectures. Now, the problem with this transmission line or propagation of wave in this transmission line is when you increase the frequency of the wave, then we have seen that the attenuation will also increase. That means you cannot propagate, or the wave cannot propagate to a larger distance when it is in a transmission line if the frequency is high, because the skin depth will come into effect, the dielectric loss will come into effect, the attenuation of the wave will come into effect. So all these things will come into effect, and if you want to transmit the wave through the transmission line for a very large distance, it is a very costly affair. Like, it will cause a lot of loss to the wave. So instead, we use something called as the waveguide. Let's say I write in short form as WG. Just like I write transmission line as TL, I write waveguide as WG. Now, waveguide is a hollow structure. What do you mean by hollow structure? Let's say I have something called as a rectangular waveguide. Okay, so for a rectangular waveguide, you will have a rectangle, okay, and then something like this. You can assume, or you can imagine it as a rectangular pipe, a hollow pipe, okay, and the wave will propagate inside this rectangular waveguide, right? So the wave which is traveling will propagate inside this rectangular waveguide in some direction. Now, the behavior of the wave inside such kind of a rectangular waveguide is entirely different from that in a transmission line or in an unbounded medium. But why we are using this waveguide? It is because for higher frequencies, the loss encountered by the wave is very less when you consider the rectangular waveguide. That's the main reason. Now, in the rectangular waveguide, you have this metallic side. So these are all metallic structures. So all these are metallic. The entire waveguide is made of some metallic elements. Okay. So what do you mean by metallic element? It has high conductivity, which means the conductivity is approximately infinity. Okay. And the inside the waveguide, which is hollow, which means this portion, this is a hollow portion, we assume it has lossless, means conductivity is zero. Okay. And when the wave propagates through this waveguide, because of this metallic structure, it will not be able to come out of the waveguide. And since there is a medium inside the container, so basically this is basically the hollow lossless medium, and then there is this metallic sheet. So there's a boundary here. This is basically a boundary for the. So when it reaches the boundary, it cannot travel outside. It will reflect it back, and it keeps on propagating. And outside it is air. So if you take a cross section of this, okay, that means if I take a cross section from here, like this, taking cross section from here, and I am looking it from this side, like this, from the side. So you see that your waveguide is something like this, and the wave is propagating something like this with reflections and everything. Okay, and wave definitely have an magnetic field and a particular electric field. Okay, but the behavior of this wave will be different. It's not like what we have seen so far. Okay, so if I say this direction is said, basically the wave is propagating. Okay, although the propagation is oblique, it is propagating slanting, and then it will reflect it here and comes back. Although this is happening, finally the wave is propagating in this direction because it is moving in that direction. So the wave is propagating in that direction. Okay, and you will have an H, which is the magnetic field perpendicular to the direction of propagation, which is currently now towards you, and there's an E field which is perpendicular to both direction of propagation and to the magnetic field. But you see that E has a component along direction of propagation, which is this. But H doesn't have a component along direction of propagation. Okay. And this is something called as a transverse electric wave. We'll see all these things. I'm just summarizing it just to give you a picture of what is going to happen. In a similar manner, it is possible that the wave which is propagating inside might have the H. Let's say I have a different wave like this. Okay, now it is possible that this wave will have E like this and H like this. So in this case, you see the H will have a component along the direction of propagation, which is this, while E will not be having a component. So this is called as transverse magnetic wave. Okay, so all these types, these are called as different modes, and all these things will come into picture. Fine. So this I just gave you an introduction of what a rectangular or waveguide is. So this is a rectangular waveguide. Similarly, I can have a circular waveguide. So circular waveguide will be something like this. You have a circle, it's like a hollow pipe, circular hollow pipe. This is a circular waveguide. Okay, and there is something called a parallel plate waveguide. So it is something like this. You have a plate like this, which goes to very long distance, and there is another plate at the bottom. Okay, and the wave will propagate in between these two plates, and there is no restriction of the wave in this direction. So in this direction and in this direction, the wave is free. Wave is bounded only at the top and at the bottom. So this is called as a parallel plate waveguide. This is called as parallel plate waveguide, and this is the circular waveguide. Okay, we will study of rectangular waveguide. Actually, the syllabus has both rectangular and parallel plate. Parallel plate is just to give you an introduction. We will study in detailed rectangular waveguide, and you can generalize. You can easily derive the expressions for parallel plate waveguide from rectangular waveguide. Okay, fine. So then let's start. So all these equations that we have seen are derived for wave in unbounded medium. We'll make use of all these things, and we will try to apply the boundary conditions, because you see that the wave propagating in an unbounded medium, when it encounters the boundary in four sides, it is basically a rectangular waveguide. So we will apply the boundary conditions on four sides of the wave to find out what will happen to the wave inside a rectangular waveguide. Okay, fine. So let's start with defining the axis, etc., etc. So let's say I have two axes. One is X and one is Y. And then I have kept a rectangular waveguide in this axis. Okay, so the waveguide extends to infinity, let's assume. Okay, but we are concerned about only the four sides. Now let's assume that the distance or the breadth of this waveguide is A. So let's say this is A. Okay, and let's say this is B. So the waveguide has its breadth from x equal to 0 to x equal to A, and its length or height from y equal to 0 to y equal to B. All are positive. Okay. The waveguide is made up of perfect metal. That means I have my metal, this is metal, all four sides are metal with conductivity infinity. This is perfect metal. And it is filled with a lossless dielectric, which means I have the conductivity inside the waveguide is 0. And the waveguide is source free means rho v is equal to 0. And there is no free current, means the J value is 0. The wave is propagating in Z direction. That to positive direction. Okay, so basically my be like this: X, Y, and Z. So the wave is going inside into the waveguide. Okay, and let epsilon be the permittivity. Mu be the permeability of the medium. Okay, so these are the setup that we are going to look at for this rectangular waveguide. Now we will start with Maxwell's equations, and we are going to use the phasor form. So consider Maxwell's equation in phasor form, which is del cross Es is equal to minus j omega mu Hs. This we have already derived. It is actually del cross E is equal to actually this is the phasor form. Now the actual equation is del cross E is equal to dou B by dou T minus dou B by dou T. And when you incorporate the phasor representation, in which we say E is equal to some real part of E0 e raised to j omega t, then you can derive that when you differentiate the actual vector, you will end up having the phasor representation of this. We have already seen this, so I am not going back and explaining everything. Okay, so this is the phasor form. So now let's expand this. Okay, so the right hand side I can write as ax cap, ay cap, az cap, dou by dou x, dou by dou y, dou by dou z. Let's assume the x component is ESX, y component is ESY, or let me other way. X EXS, y is EYS, and z is EZS. So this is basically the curl of ES, where ES has component EXS AX cap plus EYS AY cap plus EZS AZ cap. That is the ES value. So I can write in curl representation as del cross ES is equal to determinant of AX cap, AY cap, AZ cap, dou by dou X, dou by dou Y, dou by dou Z, EXS, EYS, and EZS. Now this is equal to, now you see HS can be written as HXS, the component along X, plus the component along Y, plus the component along Z. Right? Which means I can expand it to be minus j omega mu multiplied by HXS AX cap plus HYS AY cap plus HZS AZ cap. Okay, let's do left and right individually. So I can expand the left hand side as ax cap multiplied by dou EZS by dou y minus dou EY by dou Z minus AY cap into dou EZS, so this is S, by dou X minus dou EXS by dou Z plus AZ cap into dou EYS by dou X minus dou EXS by dou Y. So this is the left hand side. So this is equal to minus j omega mu multiplied by HXS AX cap plus HYS AY cap plus HZS AZ cap. I just expanded, that's all. I haven't done anything new. Okay. Now, we have some terms in the left hand side which is which we are differentiating with respect to Z. This one and this one. Okay. We know that in general, when the wave is propagating in Z direction, you have the EYS as EY0 e raised to j omega t minus gamma Z. This is general equation that we have already seen. This is the expression of electric field when we solve the wave equation. This is equal to EY0 e raised to j omega t into e raised to minus gamma Z. Okay. If sorry, this is a phasor representation. So EY is this one. When you get into the phasor, that is EY, S will have EY0 e raised to minus gamma Z, because while using phasor, you will not be taking this term. That's what all phasor is about. Now, when you differentiate with respect to Z, dou EYS by dou Z is equal to EY0 into minus gamma e raised to minus gamma Z. Similarly, dou square EYS by dou Z is equal to EY0 gamma square e raised to minus gamma Z. So dou EYS by dou Z is, this is actually minus gamma into EYS, because when you combine this and this is equal to this is EYS, then you multiply it by minus gamma. Similarly, in this case, this is equal to gamma square EYS. Okay. This I am going to substitute in my equation. Let us number this equation. So substituting in 1, implies. Now you see this is for EY. Similarly for EX, you have a similar expression, because you can represent EX is equal to EX0 e raised to j omega t into e raised to minus gamma Z, but your magnitude constant EX0 is different from EY0. So dou EXS by dou Z is equal to minus gamma EXS and dou square EXS by dou Z square is equal to gamma square EXS. Right? Because we are having that dou EXS by dou Z also in this expression, which we need to substitute. Okay, so let's substitute all these expressions in equation number 1. So I can write, let me write it at the bottom. So I can write AX cap into dou E Z dou plus gamma EYX minus y cap into dou EZX by dou X plus gamma EXS plus AZ cap into dou EY by dou X minus dou EXS by dou Y is equal to minus j omega mu into HX AX plus HYS AY cap plus HZS AZ cap. So what I did was I just substituted wherever dou EYS by dou Z or dou EXS by dou Z, I substituted the expression which we have this here, these two. Now, it is you can substitute only when there is a differentiation with respect to Z. Our wave is propagating in Z direction, because of which we will have a Z exponential Z value in our equations. Good. So let's do one thing. Let us equate the components of AX cap, AY cap, and AZ cap separately. Okay, that means we are going to equate this and this. Similarly, we're going to equate this and this multiplied by minus omega mu, and we are equating this and this multiplied by minus j omega mu. Okay, so equating the components of AX cap, AY cap, and AZ cap separately. We get AX cap or dou EZX by dou Y plus gamma EYS is equal to minus j omega mu HXS. Similarly, minus of dou EZS by dou X plus gamma EXS is equal to minus j omega mu HYS, and at the last dou EYS by dou X minus dou EXS by dou Y is equal to minus j omega mu HZS. Okay, so let me number this as 2, 3, and 4. Okay, so there is a minus sign in equation number 3 in both sides, so I'm just removing that. So there's a minus here, there's a minus here, so I just remove. Okay, so this is one set of equations. Fine. Now let's look at the next set of equations. So we are going to combine two sets of equations equation to arrive at a common solution. So in terms of a differential. Okay. So now let's next consider Maxwell's equation del cross Hs is equal to j omega epsilon es. So this is the next equation that we are going to consider. Again, I am expanding LHS, X cap, cap, A cap, dou by dou x, dou by dou y, dou by dou z, hxs, hys, hzs, its determinant is equal to j omega epsilon multiplied by exs ax cap plus eys ay cap plus ezs az. Just the same way that we have derived in the previous equations, we are going to derive a similar expression using this Maxwell's equation. The steps are exactly same. There is no much difference. Not much difference, matlab, there is no difference at all. So ax cap into dou hzs by dou y minus dou hys by dou z minus ay cap into dou hzs by dou x minus dou hxs by dou z plus az cap dou hy by dou x minus ys by dou x minus dou hxs by dou y is equal to j omega epsilon into exs ax cap plus eys ay cap plus ezs az cap. Okay. Again, we know that there are two terms which is differentiated with respect to z. Okay. And since hys is equal to hy0 e raised to minus gamma z, you have dou hys by dou z is equal to minus gamma hys. Similarly, since hxs is equal to hx0 e raised to minus gamma z, so dou hxs by dou z is equal to minus gamma into hxs. Okay. So I can substitute this in here and I can substitute this in here. So when you substitute it, you will get ax cap dou hx by dou y plus gamma hys minus ay cap dou hzs by dou x plus gamma hxs plus az cap into dou hys by dou x minus dou hxs by dou y is equal to j omega epsilon exs ax cap plus eys ay cap plus ezs az cap. Okay. Again, what we are going to do, we are going to equate the components of AX cap, AY cap, and AXL cap separately from both sides. Okay, so equating the components of AX cap, AY cap, and AZ cap separately, we get dou HZS by dou Y plus gamma HYS is equal to J omega epsilon EXS. Similarly, minus dou HZS by dou X plus gamma HXS is equal to J omega epsilon EYS. And at the last, so there's a bracket here, dou HYS by dou X minus dou HXS by dou Y is equal to J omega epsilon EZS. Let's number the equations. This would be equation number 5, equation number 6, and equation number 7. So we have got a set of some good number of equations. Let's write this set of equations together so that it will be easy for us to evaluate all these things. So let's copy this first. Let's paste here. And let's copy this first. Let's paste it here. Okay. Fine. Now, let's look at equation number 3. Okay. We can start with equation number 2, but let's look at equation number 3. So from 3, which is this one. So from 3, you have HYS is equal to, just bring this J omega to this side. So you'll have 1 by J omega mu into dou Ez by dou EZS by dou X plus gamma EXS. Okay, let's say this is equation number 8. Okay, now let's substitute equation number 8 in equation number 5. That is, I'm going to substitute this equation here. So substituting 8 in 5 implies dou HZS by dou Y plus gamma by J omega mu multiplied by dou EZS by dou X plus gamma EXS is equal to J omega epsilon EXS. Okay, we just substituted this, the expression for HYS in here. That's all. Nothing we have done, nothing special. Okay. So you see that EXS is there in both sides. Okay. So let's bring it to other side also. So just group that. But you see that there is gamma by j omega mu multiplied with gamma here, and then I need to bring it to this side. So what I get is dou h zs by dou y plus gamma by j omega mu dou e zs by dou x is equal to j omega epsilon minus gamma square by j omega mu multiplied by exs. Okay, so this is equal to minus omega square mu epsilon minus gamma square by j omega mu exs. Now let h square is equal to gamma square plus omega square mu epsilon. Implies I can write dou h zs by dou y plus gamma by j omega mu ezs by dou x is equal to minus h square by j omega mu exs. Or in other words, I can write exs is equal to, just take this to here. Okay, so I can write exs is equal to, I'm taking minus sign also to the left hand side, minus j omega mu by h square dou h zs by dou y minus gamma by j omega mu multiply j omega mu, or I can write this as gamma by h square dou ezs by dou x. And this is a very important equation. It's numbered as A. So we have found an expression for electric field component along x direction in terms of the electric field component along z direction and magnetic field component along z direction. So this both are components along direction of propagation. Okay, this is a very important equation. Now this we have seen for exs only. Okay, similarly, by looking at equation number 2, you will be able to get an expression for xs, and if you substitute that expression in this equation, you will get an expression for eys in terms of ezs and hzs. Similarly, from equation number 4, you'll get an expression for hzs sorry, you will from you can derive an expression for, from this equation you will get an expression for ezs by moving this to here, and if you substitute that in this expression, you will get an expression for hys. Similarly, eys, I can, if you move this to this side, you will get an expression for eys from this equation, and if you substitute that here, you will get an expression for hxs. So finally, you will be able to get the expression for each of the components which are not in the direction of propagation. That is, get eys is equal to minus gamma by h square dou ezs by dou y minus j omega mu by h square dou h zs by dou x. Similarly, hxs is equal to j omega mu by h square dou ezs by dou I minus gamma by h square dou hzs by dou x. As finally, hys is equal to minus j omega mu epsilon h square dou ezs by dou x minus gamma by h square dou hzs by dou y. Let's name this as equation number B, C, and D. Okay. So I would want all of you to derive this as homework. Okay. And once you come back, then once you are in the college, I will ask you to derive this in the board. Okay. So make sure you derive all these equations by yourselves so that you get a feel of how you should be able to get the expressions, because this was asked in some of the semester exams. So make sure you derive this. Okay. Fine. So we'll stop it here. I know this was, I think I have overshot it for maybe 7 minutes. That's okay. So we'll continue with the discussion in the next class, and we will have another set of derivation in the next class. Fine. Okay. So to take the attendance, let me see what are absent. ഓക്കെ, ഈ പറയുന്ന റോൾ നമ്പേഴ്സ് ഉണ്ടോ എന്ന് എന്നോട് പറഞ്ഞാൽ മതി. റോൾ നമ്പർ 1 ഉണ്ടോ? ഇല്ല. 2 ഉണ്ട്, 3, 4 ഇല്ല, 3, 4 ഇല്ല. ഓക്കെ, 5, 6 ഉണ്ട്, 7 ഉണ്ട്, 8 ഉണ്ട്, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 ഉണ്ട്, 25, 26, 27, 28 ഇല്ല, 29, 30, 31, 32, 33, 34 ഇല്ല, 35, 36, 37, 38, 39, 40, 41, 42, 43, 43, 44 ഉണ്ടോ? ഇല്ല. 45, 46, 47, 48 ഇല്ല. 49 ഉണ്ട്, 50 ഉണ്ട്, 51, 52, 53, 54, 55 ഇല്ല, 56 ഉണ്ട്, 7 ഉണ്ട്, 7, 15, 7, 59 വരെ ഉണ്ടല്ലേ. 57, 58, 59. Okay. The absent is 1, 3, 4, 28, 34, 44, 45, 46, 47, 48, 55, 58, 59. ഈ വിളിച്ച നമ്പറിൽ ആരെങ്കിലും പ്രശ്നം ഉണ്ടോ ഉണ്ടെങ്കിൽ പറയാം. ഇല്ല. Okay, fine. So we'll then end the class now, and we'll meet on Wednesday. Thank you for listening.